Hey everyone, I am Ms. Hu, your physics teacher. In this video lesson, we will be learning about electric charges, where we will cover the following topics: positive and negative charges, interactions between electrical charges, electric field, electrostatic charging, and the experiment to distinguish between electrical conductors and insulators. So before we get started, of course, we all know that Ms. Hu's slides are not complete without a meme. So here's a meme to remind you about static electricity. I'm sure you've experienced this before. Now let's get started with electric charges. Now there are two types of charges. There are positive charges and negative charges. The unit of a charge is coulomb, or you can just write the capital C as a short form. There are many different types of positive charges. One example is a proton. So a proton is a subatomic particle which has positive charge, and it resides in the nucleus of an atom. An example of a negative charge is an electron. An electron is a subatomic particle that resides in the shells outside the nucleus within an atom. There are of course more examples of these charges. These are just one example of each type. By now, you should have learned about the subatomic particles of protons and electrons. So you should know that one proton has a relative charge of positive 1, while one electron has a relative charge of negative 1. Now, we use the term relative here because relative means comparing to one another. You need one electron to neutralize one proton. So one proton, one electron, you'll get a neutral charge. But in physics, when we talk about measurements, there are also very exact numbers that are ascribed to those physical quantities. Now, charge has the unit of coulomb, and the value of the charge of a proton and electron are not 1 coulomb respectively. The actual value is this. The charge of one proton is positive 1.6 times 10 to the power of negative 19 coulomb, while the charge of one electron is the opposite, negative 1.6 times 10 to the power of negative 19 coulomb. Now don't worry, you're not expected to memorize these numbers. If you need to use the number in any equation, the value will be given to you in your examination paper. Before we move on, let's look at the electric field around the individual positive and negative charge. What is an electric field? The electric field is defined as the region where an electric charge experiences a force. You need to know when we draw the directions. The direction of the electric field at a point is based on the direction of the force on a positive charge at that point. What do we mean when we say force? Now, you need to know that same charges repel while opposite charges attract. That means that if you put a positive charge next to a positive charge, the charges will repel. And the same applies also if you place a negative charge next to a negative charge. However, if you place a positive and negative charge next to each other, they will attract. So the forces that we are referring to here are the forces of repulsion and forces of attraction that causes the charges to move. Now, how we draw the charges is this. The positive charge has a field that's acting around it. So you draw lines in all directions. I know my lines are not straight, so imagine they're straight. So when you draw them, you need to draw them straight. Okay, for the positive charge, the force is acting outwards in all directions in the electric field. For a negative charge, it's the opposite. So you will have radial lines also coming out from the negative charge, and they're going inwards from all directions. Okay, I'm going to fix this a little bit because it's not straight. They have to be straight lines. And when you draw the radial lines, make sure that the space between the lines are even. So these are the electric fields around a single point charge or a charged sphere. When you place the charges next to each other, the field lines are going to interact. You must remember that the field lines cannot cross. Okay? They may join together, they may move away from each other, but the lines cannot intersect. So on this slide, we have 3 pairs of charges, and we're going to learn how to draw the electric field between these 3 pairs. So we have a pair of positive and negative charges, a pair of positive charges, and a pair of negative charges. So how do we draw the field lines? Now, observe first before you start drawing. Now what I'm going to do is I'm going to explain step by step how the lines are obtained. You don't have to do this in your actual examination. You can just draw the final result. But I'm going to show you how to come up with the field lines in the first place. We will start first with the top pair of the positive and negative charge. As we know, for positive charges, the field lines are radiating outwards in all directions, while for the negative, the field lines are radiating inwards from all directions. Now remember that the field lines cannot cross, they cannot intercept. I'm just going to fix the lines a little bit. As you can see, you have lines in between the positive and negative charges here that seem to be moving in the same direction, which means that they can actually combine to form a continuous line. So the line in the middle here will end up joining together to make one line. So I'm just going to erase that and redraw to make it look better. So you'll have one straight line in between moving from positive to negative. Now for these lines, there's a diagonal line moving out and away and a diagonal line moving inwards, which means that they can actually combine to form a curve. And the same applies also to the line at the bottom. So if we were to draw this properly, you would get a curved line on the top and a curved line at the bottom like this. That's why the lines are curved. They're actually diagonal to begin with, but then they end up combining because they're moving in the same direction. So this is the electric field between two opposite point charges. Now let's look at what happens in the pair of positive charges. So again, observe first. You'll find that for positive charges, the field lines are going outwards in all directions. So I'm just drawing the field lines first so that you can visualize what's happening. And in this case, because they're both positive, you find that both will have field lines moving outwards, and none of the field lines can combine because they're all going outwards. Field lines cannot intercept. So what's going to happen is that the lines here are going to end up pushing away from each other. You can even see in the middle here, they're going to clash with each other. They cannot combine. So as a result, you'll find that the overall field line would look like this. So in the middle, we normally remove the field lines because they end up going away from each other. So it creates a region where there's no field lines. So how we normally draw this in the end is to show that the field lines will push away from each other, leaving a region where there's no electrical field. Once you understand how the field lines are formed for two positive charges, you should understand that the shape would be exactly the same for negative charges. It's just that they are in the opposite direction. For the negative charges, this time, the field lines are moving inwards towards the negative point charges. And that's how we draw the field lines. Do take note that when you draw the field lines, the lines must touch the surface of the sphere and the lines cannot go inside the sphere. So do not draw lines crossing inwards. That would be incorrect. Now besides spheres, you also need to know how to draw the field lines between parallel plates or plates and point charges. So on this slide, there are three diagrams with which we're going to learn to draw the electric fields of. Let's start with the diagram on the left. So on the left here, we have two parallel plates. One plate is positive and one plate is negative. So as you can see that the plate has a flat side, which means that the lines are going to come out parallel to each other. So again, even spacing between the positive and negative plates. So they're all parallel. And at the corners here, you have to understand that for positive charges, the field lines go outwards in all directions. So that means the corner here, there'll be a diagonal line going up. And for the negative, there's a diagonal line going inwards. And they're going to combine to form a curve at the edge. So right at the corners here, there'll be a curve. So that's why you get this kind of shape between two parallel plates. Now if you have a flat plate and a sphere, this is how you get the diagram. So I'm going to break it down again. For the flat plates, we know that the field lines are going to come out parallel. While for the negative point charge, we know that the charge is going to have field lines coming in from all directions. So obviously, the field lines are going to move from positive to negative, and you should be able to see that the lines will be able to combine. So the line in between these two will end up being a straight line here. So I'm going to erase this and redraw to make this nice and clean. So it's one line from positive to negative, like this. Now, the field line above and below it, you can see from the positive plate it's straight line, but into the negative, it's a diagonal. So you're going to find the lines are going to curve. So it's going to be straight and then curves into the sphere, like that. I'm just going to clean this up. So straight line and then curves in. Straight line and then curves in. So you'll find this is also true for the lines that go slightly higher. You'll have a straight line coming from the plate and then curves into the sphere and like so. So this explains why the shape of the electric field looks like this. For the other arrows, we're not going to combine it because they're already too far. For the field between the positive point charge and the negative plate, again, same shape but opposite direction. So now the field lines are going to go from the positive point sphere to the negative. So the line will come out from the positive at a curve, then angle, and then go straight into the negative plate. And it's a curve like that. It's going to go up, curves and goes in, curves and goes in, like so. So that's the electric field between two parallel plates and a plate and a point charge. Now, in addition to knowing what an electrical field is and how to draw it, you also need to know that the lines are not randomly drawn. When we draw the lines, visually, the lines should show how strong the electrical field is. So the greater the density of lines, the stronger the electric field is. That means that the spacing between the lines is lesser. The lines are closer to one another. So for example, if we were to compare two point charges like these, where both are positive, we know that for a positive charge, the field lines are radiating outwards in all directions. So the standard drawing we would draw, of course, is to draw radial lines outwards in all directions. So normally we would draw 8 lines. But say we have another point charge here that's also positive, but it has a stronger electrical field. How would we represent that this point charge has a stronger electrical field? Because it's positive, this means that it will also have radiating lines outwards in all directions. To show that it has a stronger electrical field, we would draw more electrical field lines radiating from the point charge. Again, remember that the spacing must be even. So the more electrical field lines there are, the stronger the electrical field. So this is how we can visually show that electrical field is stronger. So this is true in all electrical field patterns that you need to draw. So to give you another example, if we have two parallel plates, to show that the electrical field is stronger, we would need to draw more lines. So for the pair on the left, you can see the electric charge is a bit less, which means the electrical field will be weaker. So we're going to draw less lines here just to show that the electrical field is weaker. While for the diagram on the right, to show the electrical field is stronger, we would draw more lines. So that's how you can visually determine whether the electrical field is stronger or weaker. Now, what we've looked at so far are the electric field around shapes that are quite regular, where the electric field has an even distribution of strength around them. It is also possible sometimes that you may get an object or a material where the electric field strength is not evenly distributed. So I'm just going to draw one here just for visualization. For example, you could get a metal object which has a tip like this. Let's say that this object is positively charged. So on the surface, you'll have positive charges distributed around it. Now, the thing is, the electric field may not have evenly distributed strength here because of this point. There is a concentration of positive charges over here. As you can see, the positive charges are much closer together compared to at the bottom. So even if I were to draw the positive charge distribution around, trying to make it as even as possible, you'll find that at the tip, there will still be a greater concentration of positive charges, which means that the electric field at that point may be stronger compared to the rest of the surfaces, even though it's on the same object. So you could have a positive field around the object, which is not evenly distributed. It actually gets stronger at the tip. So again, how you can represent that the strength of the electric field is greater there, the density of lines have to be greater. That means the spacing between the lines is less. Now, let's go on to electrostatic charging. So what is electrostatic charging? It is a process where materials acquire a net electric charge, either positive or negative, due to the transfer of electrons. You need to know, of course, that during electrostatic charging, only electrons move. Electrostatic charging occurs due to the friction between two insulating materials. This is because friction can cause some of the electrons to be physically moved away from their outermost shells. Now note that this only works with insulating materials because unlike conducting materials, insulating materials do not have electrons that move freely. So in order to be able to move them, we have to physically move them through the process of friction. You'll find that some objects are more attractive to electrons than others, causing the electrons to move from one material to another. So, for example, if you were to rub a plastic rod with a wool cloth, the plastic rod will tend to attract electrons from the wool cloth. So if you took a wool cloth and you rub the plastic rod, the wool cloth will tend to lose electrons and the plastic rod will gain electrons, meaning that the electrons will move from the wool cloth to the plastic rod. Because there's been a net movement of electrons, the plastic rod would end up being negatively charged, while the wool cloth will be positively charged. So whenever we compare two objects, one object will tend to attract electrons more than another. So don't think that, oh, a plastic rod is guaranteed to be negatively charged all the time. It depends on what material it is interacting with. So between two objects, there will always be one that tends to attract electrons more than the other. Now let's go into how to detect electrostatic charges. There are two methods which we're going to learn. The first method is a really simple experiment. What you do is you suspend one of the insulating materials using a cradle. So you can even try this at home. Use a piece of paper to just make a simple cradle like this. Place a plastic ruler here and suspend it using a string. For example, you can just hold it up or tie it to an object in order for the material to be able to freely rotate. Rub one end of the material, the cloth, in order to give it a charge. Now you take another piece of insulating material and charge that by rubbing with the cloth, and you hold the charged end of the second piece close to the end of the first piece. If you find that a freely rotating material rotates away, that means the materials have the same charge. Whereas if it moves towards the second piece, then they have opposite charges. If there is no movement, then there's no electrostatic charge. So here is a bigger version of the image, and you can even try this at home. Now another method that you can use is to use a gold leaf electroscope. So what's a gold leaf electroscope? You would find this in a school lab. The gold leaf electroscope basically is made up of a metal disc outside and it's connected to a metal strip that's inside a glass chamber. So normally the chamber is necessary to prevent outside charges from interfering with the metal strip inside. On a metal strip, you'll find there is a piece of gold foil or gold leaf. That's why this is called a gold leaf electroscope. So the reason why electroscopes use gold is because gold is an excellent conductor. The electrons move very easily on the surface of gold, and by using a very thin piece like a leaf, the leaf is able to move very easily. So that means that the movement of electrons is so quick that the gold leaf is able to react instantaneously. This piece of gold leaf is connected to the metal strip only at the top here. The gold leaf is free to move, and you can see that this electroscope even has an angle measurement here, a sort of protractor, where we can observe and even record the angle at which the gold leaf would move. So how do we use the electroscope to detect electrostatic charges? Now, if the electroscope is discharged, the gold leaf will be down. That means the gold leaf would not move upwards, it will stay down because there are no charges, therefore no attractive or repulsive forces. So the word discharged here means to remove all the charges. Now, if you bring a charged object near the disc, not touching it, the gold leaf would move up. Let's talk about the first part and why. So the reason for this is because if you were to bring a charged object here, whether it's positive or negative, it doesn't matter. But I'll explain first with a positive charge. So if you bring an object that's positively charged near the disc, what happens is that it'll attract electrons. So electrons in the metal strip and the gold foil will end up moving upwards because they are attracted to the positive charge. So that causes the strip and the foil to be positively charged. So if I were to draw a bigger diagram here, you imagine that now they're positively charged. Remember that the gold leaf can move and it's only connected at the top here. So positive and positive, what happens? That's right, gets repelled. So you'll find the gold leaf will move up. So of course, if there is a greater attractive force, then that means that the gold leaf and the metal strip will have an even greater positive charge, causing the leaf to move up even higher. What if we brought a negatively charged object near the electroscope instead? The leaf will still move upwards because this time it will push electrons to move downwards, causing the strip and the foil to be negatively charged. And again, what happens when it's negative and negative? That's right, the foil will also be repelled. So again, it will move upwards. So whether you're bringing a positive charge or negative charged object near the disc, it will still cause the gold foil to repel and therefore move up. So now let's look at the second part of this slide. If the electroscope was already charged, the gold leaf will be up. That means before we even start the experiment, we would already charge the gold leaf electroscope, meaning that the foil will already be upwards. So if you bring a charged object near the disc, the gold leaf will move even higher if it has the same charge. So for example, if the strip and the foil are already positively charged, you bring a positively charged object nearby, it causes electrons to move upwards. So when the electrons move upwards and away from the strip and the foil, there's a greater positive charge on both the gold foil and the strip. So with stronger positive charges, there'll be a greater force of repulsion. That's why the gold leaf will move higher. Now you bring a negatively charged object near it, it's going to cause electrons to move downwards. So when the electrons move downwards, they end up neutralizing the strip and the foil, which is why the foil ends up moving downwards instead. So the gold leaf will drop. So this is how you can use a gold leaf electroscope to detect the presence of electrostatic charges and even to determine whether they have the same charge or opposite charge. Here's a picture I took of an electroscope in my school lab, and here's a video you can find on my YouTube channel which shows how the gold foil on the electroscope will move. Now let's talk a little bit more about conductors and insulators. Electrical conductors are materials which allow electrical current or electrons to flow through easily. So metals are usually good electrical conductors because they have delocalized electrons, or you can say free electrons or free moving electrons. So examples of conductors are of course different kinds of metals, for example copper, gold, and so on. Electrical insulators, on the other hand, are materials which do not allow electrons to flow through. And the reason for this is because insulators do not have delocalized electrons. That means they do not have free electrons. Electrons are not free to move. So examples of insulators are of course non-metals such as glass, wood, rubber, paper, and so on. So that's why when we talk about electrostatic charging, this only works with insulators. Because if we look at the term electrostatic, static means what? Not moving. So the term electrostatic charging here means that although there are movement of electrons, there has to be a process that have moved the electrons, for example, through friction. So friction has moved the electrons, and once we've moved the electrons away, the electrons stay where they are. For example, the electrons stay on the plastic rod. They don't jump back to the wool cloth easily. So that's what we mean by static electricity or electrostatic. Electrostatic charging doesn't work with conductors because electrons move too easily. So you can visualize it this way. If you apply friction to try to move the electrons from one point to another point, the electrons move so easily that they don't stay there, they just flow back to where they came from even before you actually lift and separate the materials from each other. So that's why you find the process of electrostatic charging does not work on conductors, it only works on insulators. Now let's look at how to distinguish electrical conductors and insulators. Again, we just go through two simple methods. The first method is something that many of you would already know by using a simple electrical circuit. First, all you need to do is connect a simple electrical circuit using a power supply, for example a cell or a battery, use a light bulb, and connecting wires with connecting leads or crocodile clips. Leave an empty space as shown in this circuit diagram. Place a material that you want to test between the connecting leads, and if the light bulb lights up, that means the material is a conductor, and if it's not, it is an insulator. Another method is by using the gold leaf electroscope. Now how we use the electroscope in this case, we charge the disc of the electroscope so that the gold leaf stands clear of the rod. Next, carefully touch the disc of the electroscope with the items being tested. So this time, instead of just hovering, we actually touch the disc with the items that we want to test. The results that you get will indicate whether the material is a conductor or insulator. So if we observe that the leaf falls, that means that the material is a good conductor. And the explanation for this is because electrical charges are able to flow between the disc and the object. So the direction that they flow in depends on which object is more negatively charged. Why is this indicative that the material is a good conductor? Because if the charges are able to flow, that means the strip and the gold leaf will end up being neutralized, and that's why the leaf would fall. Now, if the leaf does not fall, meaning it doesn't move at all, this means that the material is a bad conductor or a good insulator. And that's because electrical charges do not move, hence there's no reaction at all. Now, if we observe that the leaf does fall, but slowly, this means that the material is able to conduct electricity, but poorly. So the electrical charges can flow, but they flow slowly, either from the disc to the object or from the object to the disc. And that is it for this video. So, if you found this video to be educational and helpful, do click like and let me know in the comments below how you have found this video to have helped you. If you'd like to help me keep making free educational video lessons and lab practicals, donations are welcomed at my Ko-fi page. That's ko-fi.com/physicsrocks. For notes, quizzes, and syllabus updates, check out my website at physicsrocks.com. Do watch my videos on other topics on my YouTube channel which you might find helpful. Subscribe for more free physics lessons from your physics teacher, Miss Ho. Happy studying!